Hello, welcome back to Our Universe. I'm Jeff Connell, and today we'll be exploring galaxies. We'll find out what they are, how they formed, what shapes they come in, what happens to them when they collide, and then we'll talk about the James Webb Space Telescope that recently launched and what amazing new technology it's carrying that will allow us to look back in time to when galaxies were just forming around 13.5 billion years ago. All exciting stuff, so let's get to it. Today we're traveling through intergalactic space. I'm not talking about the space between planets or even the space between stars. No, we're traveling through the space between galaxies. Joining us today is our ship's computer. I'll be communicating with it through its Virtual Intelligence Kernel Interface, or Vicky for short. Vicky, do you want to say hello to everyone?
Yes, I do.
Okay, go ahead then.
Hello to everyone.
Can you still say a little bit more? If you want.
A little more than that if you want.
No, if you want to say anything more to our audience, please feel free to do so.
Oh, in that case, it's a pleasure to meet you all.
Much better. Can you tell us where we are right now?
Yes, I can.
Okay, let's reword that. Vicky, can you tell us where the ship is located right now?
We are here.
Can you be more specific?
Yes, I can.
Vicky, what is your current setting for interpreting literal context?
8.
Bring it down to 6.
Done.
Okay, let's try this again. Tell us where we're located.
We are currently located 2.5 million light years from the Milky Way galaxy and an equal distance from the Andromeda Galaxy. From this vantage point you can see both galaxies outside the ship's window.
Okay, well let's take a look. Okay, I can see the Milky Way on the left and there's Andromeda on the right. Wow, this view is really awesome. Vicky, what are all these other points of light?
Each point of light is a galaxy.
Can you expand so we can see more detail?
No, I'm afraid my microprocessor is unable to expand outside of its housing.
Was that an attempt at humor?
No, I am truly unable to expand.
Okay, let's try this then. Vicky, expand a small section of our view so we can see more detail.
Here you go.
All right, wow. How many galaxies are we looking at here?
This section of sky contains 4,000 galaxies.
And what portion of the sky does this represent?
This view represents 1/50 millionth of the total view around us. It would be equivalent to the size of your credit card held 400 feet away. I could show everyone what your credit card looks like at this distance, but for your security, I advise against it.
Good call, Vicky. Hey, if we expanded the view of each of the 50 million sections of sky that surround us, how many galaxies would we see?
We would see approximately 200 billion galaxies.
And how many stars is that?
That would be a lot of stars.
Can you be more precise?
No, I cannot.
Why not?
That precise data does not exist at this time.
Okay, then can you give me a close approximation?
Each galaxy contains on average 100 billion stars, and there are approximately 200 billion galaxies, so there are approximately 20 sextillion stars in the visible universe.
That's like a 20 with 21 zeros after it. Is there an easier way to visualize how many stars that is?
Here's a comparison that might help. There are approximately 4 times as many stars in the universe as there are grains of sand on all beaches on all of planet Earth.
Yep, that definitely lends to a better understanding of just how immense our universe is. All right, so we're talking about galaxies today, so let's get to it. Vicky, can you help with graphics?
Yes, I can.
Vicky, will you help with the graphics?
On it.
Thanks. Before the 20th century, the topic of galaxies, in the plural sense, never really came up. People generally believed that the stars that we saw in the sky were our universe, the entire universe. And throughout history, galaxies have always been visible in the sky. It's just astronomers believed that they were fuzzy-looking gas clouds, which they called nebula. By the turn of the 20th century, it was becoming clear that some of these nebulae were something different. And then on December 30th of 1924, Edwin Hubble announced his discovery of the Andromeda Galaxy. A few weeks later, he presented his findings at an American Astronomical Society meeting. To support his claim, Hubble calculated the distance of Cepheid variable stars inside of Andromeda. At the time, calculating the distance of Cepheid stars was a relatively new science. It had been just 16 years earlier that Henrietta Swan Leavitt first discovered the relationship between the brightness of Cepheid stars, the length of their brightness cycle, and the relative distance away that they were. Applying Leavitt's calculations and leveraging the largest and most powerful telescope in the world at the time, Hubble calculated the distance of several Cepheid stars within Andromeda. To his amazement, he discovered that those stars were an order of magnitude farther away than any of the Cepheid stars in our galaxy. I can't stress how significant this discovery was because the universe suddenly became much larger than anyone ever imagined at that time. Today it would be equivalent to identifying another universe. In fact, in the 22 January New York Times article, the headline read, "Another universe seen by astronomer." This discovery also presented us the first clear view of our own galaxy, or at least what it might look like from the outside. And as we would learn later, Andromeda and the Milky Way actually do have a similar shape. From the discovery of the Andromeda Galaxy, astronomers went on to discover another 1.5 million galaxies. In fact, at this point, the astronomical community's ability to catalog new galaxies is limited not by their ability to find them, but instead by the time it takes to catalog them. Here's what I mean. Let's say it takes 1 second to catalog a new galaxy. By catalog, I mean jot down some basic information about it, like its position in the sky, the general shape of the galaxy, its distance from us, and of course, we have to give the galaxy a unique name or identifier. Okay, I'm pretty sure that this process for each galaxy is going to take more than a second, but for the sake of making my point, let's say we could catalog one galaxy every second of every day, 24 hours a day, 365 days a year. At this blazing rate, which remember I said probably is not even possible, it would still take 6,000 years to catalog the roughly 200 billion galaxies that exist in the visible universe. Okay, now that we know that galaxies are everywhere and that they're so numerous that it's a challenge to catalog them all, let's talk about how they came about. For this, we need to go all the way back to the beginning of time. The Big Bang is the most widely accepted theory explaining the origin of the universe and therefore the origin of time. The basics of the theory are fairly simple. Before the Big Bang, the entire universe was contained inside an infinitely dense point called the singularity. About 13.8 billion years ago, for reasons astrophysicists are still trying to unravel, the singularity started to expand at a very rapid rate. When I say rapid, I mean expanding from something like 1 nanometer wide, which is about half the width of a strand of DNA, to 10 light years across in an instant. In that first tiny fraction of a second when the universe was expanding faster than it is even today, it started off hot, like 100 million trillion degrees Fahrenheit hot. The only forms of matter that can exist at that temperature are quarks, gluons, and electrons. As the universe expanded, it followed the first law of thermodynamics, which basically means it cooled proportionally with the expansion. At around the 1 second mark, the universe had expanded to around 20 light years across, and temperatures had dropped to around 18 billion degrees. At this temperature, quarks were able to combine to create neutrons and protons. At around the 3-minute mark, the universe had cooled all the way down to about 1.8 billion degrees, and it was 600 light years across. At this temperature, neutrons were able to bond with protons to create the first atomic nuclei. This process lasted for about 17 minutes and was called the Big Bang nucleosynthesis. At the end of 17 minutes, the protons and neutrons that filled the universe were transformed into around 75% hydrogen and 25% helium nucleons, along with a few other trace isotopes. Now remember, even though neutrons and protons were now bonding together to form nuclei at this point, the universe was still too hot for electrons to attach themselves to those nucleons to create atoms like we know them today. The universe was also dark at this point because photons can't travel straight for very long in a field of positively charged nucleons and negatively charged electrons. They keep bouncing around off of each other. The period of darkness lasted until the universe cooled down to around 5,000 degrees Fahrenheit. At this point, the universe became cool enough for electrons to bind to the abundance of nucleons to create the very first atoms in a process called recombination. the universe suddenly started to fill with clouds of electrically neutral hydrogen and helium atoms. And because the atoms were neutral, photons were now able to fly free of obstructions. So there was also light in the universe for the very first time. And here's something amazing. We can still see that first light. The photons emitted in that early universe still fill the universe today and can be detected by infrared and radio telescopes in every direction we look in what's called the cosmic microwave background. Over the next 100 million years, gravity was compressing large areas of this hydrogen and helium gas into enormous clouds. As these clouds compressed even further under their own mass and gravity, pressures and temperatures within them rose to a point where atomic fusion was able to occur at the densest points within the cloud regions. This is where the universe entered the next phase of evolution, the creation of stars. I recorded an episode called The Formation of the Solar System that explains this process if you want to check it out. It's fascinating. But as we fast forward to around 200 million years now after the Big Bang, stars were sparking into existence everywhere within these clouds that were scattered across the entire universe. A few billion years later, the clouds evolved into enormous islands of stars, each island a galaxy held together by the gravity of the stars themselves. Gravity also pulled galaxies together into loose clusters. Our galaxy is a member of one of those clusters, a cluster called the Local Group, containing approximately 54 galaxies. If we zoom out from our cluster, we find that it's also a member of a neighborhood of clusters, around 100 of them, in a larger system called the Virgo supercluster, which is also loosely held together by gravity. If we zoom out even farther, we discover that the Virgo supercluster is just one of 10 million superclusters that span the entire visible universe. But a strange thing happens at distances that separate superclusters. Gravity is overpowered by an opposing force called dark energy. Dark energy pushes things apart. It's the force that astrophysicists believe is causing the universe to expand faster and faster. Gravity and dark energy are constantly engaged in a cosmic tug of war. Whether a particular area of the universe is expanding or contracting depends largely on which force is dominating the space. The dominating force is controlled by distance. At distances existing within a supercluster, gravity is stronger, so the supercluster holds together. However, at distances that separate superclusters, dark energy wins out over gravity. From a universe-wide perspective, gravity is pulling together regions of matter, while dark energy strings those regions out along filaments that are stretching out in every direction. The combined effect is what is called the cosmic web. Okay, now that we understand the basics on how galaxies form, let's talk about the sizes and shapes they come in. Galaxies come in all sizes. The Milky Way happens to be average in size. It's about 100,000 light years across, and it contains somewhere between 100 and 200 billion stars. However, galaxies can be both much smaller and much larger than ours. For instance, the smallest galaxy discovered to date is a dwarf galaxy called Segway 2. It's located just past the edge of our galaxy, which is why we discovered it, and it only contains about 1,000 stars. This is a picture of it. You really can't see it. It's only 221 light years across, and although it looks more like a group of stars, those stars are gravitationally bound to each other the same way that the stars in our galaxy are. So it technically is a galaxy. Now compare Segway 2 and the Milky Way to the largest galaxy discovered so far. This supergiant galaxy goes by the name IC 1101. It's located 1 billion light years away, it's 2 million light years across, and it contains around 100 trillion stars. It also has a bright radio source at the center, which might be evidence of the largest black hole in the universe. And by the way, this is another characteristic of galaxies. Astrophysicists believe supermassive black holes lie at the center of virtually all galaxies, even our own Milky Way. While an average-sized black hole contains the mass of around 10 of our suns, supermassive black holes can be millions or even billions times larger. Technically, we can't see black holes because their gravity is so strong that even light can't escape their grasp, but astronomers can detect them by watching their gravitational influence on nearby objects. The supermassive black hole at the center of our galaxy was confirmed when astronomers observed a star orbiting an invisible object at a very fast speed. Using this star, they were able to calculate that the black hole, which they've named Sagittarius A, has a mass 4 million times greater than our sun, and it's 14 times wider than our sun. And while we can't see black holes directly, we can sometimes get a glimpse of their shadow. In 2019, an international team of astronomers snapped this picture of the shadow of a supermassive black hole located 53.5 million light years from the Milky Way. This behemoth, located at the center of galaxy Messier 87, has a mass 6.8 billion times that of our Sun, and a diameter that's larger than our solar system. As matter is drawn into the black hole from nearby stars, gravity and angular momentum create a accretion disk. Most of the accreted matter will ultimately become part of the black hole, but a small percentage of it will get accelerated to near the speed of light and then be shot out along the axis in the form of X-rays, which will shoot out across the universe. This is a wider shot of the same black hole, and as you can see, one of the jets spewing energy from beyond the galaxy itself. The other jet is hidden on the other side of the galaxy by gas. Although galaxies come in many shapes, astronomers tend to group them into one of three categories or shapes. They're either spiral, elliptical, or irregular. Around 70% of galaxies have a spiral shape. Spiral galaxies are flat, spinning disks around a higher density central star region. As name implies, the disks of most spiral galaxies are spiral-shaped, although they don't have to be. How the spirals form was a puzzle to most astrophysicists for decades. So around 10 years ago, astrophysicists created a supercomputer simulation where they invoked the motion of 100 million simulated stars and gas clouds. The simulation demonstrated that the spiral structure is completely natural. Apparently, all you need is gravity and something that perturbs it. In the case of spiral galaxies, the mass of the galaxy provides the gravity, and when you introduce interstellar gas and dust, that's all you need for the spiral arms to form and maintain their shape indefinitely. While spiral galaxies look like spinning disks, elliptical galaxies look more like spinning spheres, except that they're stretched out more on one axis than the other. This beautiful image shows three galaxies located in the Draco constellation. They're called the Draco Trio. Can you tell which one is the elliptical galaxy?
Yes.
Sorry, Vicky, I wasn't asking you that question. I was asking our audience.
Sorry.
It's okay. My bad for not being more specific. Okay, if you pick the galaxy in the middle, you're correct. The two galaxies on either side are spirals. Astrophysicists believe elliptical galaxies may have formed from the merger of two or more larger galaxies. During mergers of this scale, stars get thrown about randomly, giving the galaxy its elliptical shape. Galaxies that aren't spiral or elliptical fall into a category called irregular galaxies. Irregular galaxies, such as the large and small Magellanic clouds that flank our Milky Way, as well as Segue 2, which hangs out just past the edge of our galaxy, lack any distinct shape. Astrophysicists believe this is due to the gravitational influences imbued by the nearby larger galaxies. They basically never have a chance to form their own shape. By the way, what I mentioned about galaxy mergers isn't just theory. Astronomers can see mergers occurring in real time across the universe. Astronomers believe that as many as 25% of galaxies are currently merging with other galaxies, and probably even more are gravitationally interacting with their neighbors. In fact, our galaxy likely formed from a series of mergers with smaller galaxies and star clusters over the past 13 billion years. Future mergers are also expected to occur. The Large Magellanic Cloud is expected to merge with the Milky Way in about 2.4 billion years. Eventually, all the dwarf galaxies that flank our Milky Way will merge with it. Because these mergers will be relatively small, they won't necessarily change the shape of our galaxy to any great extent. However, our inevitable merger with the Andromeda Galaxy will. The Andromeda Galaxy is also known as Messier 31. It's a spiral galaxy like our own. It received its name from the area of the sky that it was discovered, which is near the constellation Andromeda. To me, it looks more like a star with a fuzzy halo around it, but you can find it. I personally find it by looking for constellation Cassiopeia, which is easy to find because it's shaped like a skewed W. The right side of the W, the deeper side, acts like an arrow pointing in the general direction of the Andromeda Galaxy. Let's see if you can do this yourself. Do you see Cassiopeia in this image? I'll give you a second.
Yes, I see it.
Thanks, Vicky. Somehow I knew you could find it. If you found it like Vicky did, you'll have no trouble finding this constellation in the night sky. Once you find Cassiopeia, follow the direction of the part of the W that looks like an arrow, and you'll see the Andromeda Galaxy. Of course, it's easier to see if you're in a dimly lighted area like in the countryside, but you won't need a telescope or even binoculars because the Andromeda Galaxy is actually 6 times wider than the moon in the sky. Andromeda is the second largest galaxy in our local group, the most massive being our Milky Way. Astronomers used to think it was the other way around until 2019, when NASA and the European Space Agency confirmed that the Milky Way is close to 1.5 trillion solar masses, while Andromeda is around 800 billion solar masses. So this gives the Milky Way about twice the mass of the Andromeda Galaxy. Another very interesting fact about the Andromeda Galaxy is that we're on a collision course with it, or it with us, or with each other, or however you describe a collision in space. NASA created this simulation that shows what that collision might look like, covering 8.2 billion years at a speed of 105 million years per second. This simulation shows that in approximately 4.5 billion years, our two galaxies will collide nearly head-on, passing by and through each other several times, each collision throwing stars about in every possible orbital direction. The spiral arms of both galaxies will stretch and warp with each pass. The supermassive black holes of each galaxy will dance around each other and may even merge into one. Interstellar gas and dust thrown about during the merger will eventually fall back towards the center region of the galaxy, creating new stars along the way. The newly created galaxy will eventually settle into an elliptical shape because there's no longer enough interstellar gas and dust to form spiral arms again. As Vicki mentioned earlier, NASA estimates that there are around 200 billion galaxies in our universe. That estimate was extrapolated from the population of galaxies discovered so far. This famous image, which is called the Hubble Extreme Deep Field or Ultra Deep Field, was assembled from 10 years of photographs of a tiny area of space in the Fornax constellation. This is not actually just one photo, it's a montage of images taken at various exposures so that the farthest and faintest galaxies could be seen. In fact, the faintest galaxies in this image are 1/10,000,000th the brightness of what a human eye can see. The picture also contains overlays taken in both visible light and infrared. The resulting picture, representing a field of view equivalent to 1/10 the width of a full moon, contains more than 5,000 galaxies. What I think is most incredible about this picture, though, is that the farthest galaxies in it are not as they look today, but as they looked 13.4 billion years ago. This is because the farther away a galaxy is, the longer it takes for the light to reach us. The farthest galaxy identified so far is GNZ11. Because this galaxy is so far away, and because of Hubble's current optical limitations, we don't see much detail. And details would be super helpful because they could help us understand how our galaxy formed in the dawn of the universe. But what if I told you that soon we'll be able to turn this image into this? Now, this is an artist's representation, but what if I told you we just launched a space telescope that will enable us to see many more, this one and many more other galaxies that are even further away? The James Webb Space Telescope was launched on December 24th of 2021, and it's an exciting telescope. The James Webb improves on the Hubble in two important ways. First is the size of its mirror. Think of a telescope mirror like a light bucket. The greater quantity of light it can collect, the farther away it can see, and with greater detail. The James Webb has 18 hexagonal mirrors that have a combined diameter of 21.3 feet. It will have 6 times the light collection capability of Hubble. The camera on board the Webb has 15 times the field of view of the Hubble and has much greater resolution. The Webb's other major advantage is the type of light it can collect. The Hubble Space Telescope collects visible light, ultraviolet light in a narrow band, and some infrared. The Webb is primarily an infrared telescope, but more importantly, a wide-spectrum infrared telescope. The reason why infrared is critical when looking at objects far away is because the universe is expanding. And this has the effect of stretching light waves. As light waves stretch, they become red, and then they eventually disappear. And this is the reason why the farthest objects visible to the Hubble look like red blobs. While Hubble can look back in time when the universe was 400 million years old, the James Webb will allow us to look an additional 150 million years back to when the universe was 250 million years old. While 150 million years difference may not seem like a lot, in the words of University of Texas professor and astronomer Caitlin Casey, it's the difference between seeing the first stars that ever turned on and arriving a bit too late after the funeral. Webb's infrared detection capability will have other uses as well. It's exactly the type of capability you need when studying exoplanets. If you're on a planet orbiting another star and want to see Earth, visible light is not the best bet to catch us. The Earth would be better seen in infrared. Scientists plan to use James Webb to analyze the atmosphere of other worlds that are located in habitable zones of other stars. The James Webb will be able to determine if their atmospheres contain water, carbon monoxide, carbon dioxide, and methane. And while these molecules are not definitive signs of life on other planets, they could open the door to further study with future telescopes. Since its successful launch on Christmas Eve, the James Webb has been safely transported to a special spot called the Second Sun-Earth Lagrange Point, or L2 for short. This spot's around 940,000 miles from the Earth, which is around 4 times the distance of the Moon. If everything goes as planned, Webb will be in place, sending us some amazing images around June of 2022. I'm really excited about this mission. I remember when the Hubble Space Telescope sent its first clear images to Earth in the early 90s. It was a huge jump in image resolution. To show you the difference back then, here's an image of galaxy NGC 3370 taken by a ground-based telescope in 1994. Many of the features are blurred because the Earth's atmosphere is preventing us from seeing it very well. And the Hubble Space Telescope, which sits above the distorting atmosphere, allowed us to see much greater detail. But the James Webb has a much larger mirror and the capability to see in a wide spectrum of infrared. It will allow us to see galaxies and stars as they formed in the earliest period of the universe, and it will give us a better understanding of how galaxies, including ours, formed from giant clouds of atoms into what they are today. Okay, that's all I have today. I hope you enjoyed this episode. If there are areas of the universe you would like me to explore, let me know in the comments below. And please share this episode with friends and family if you think they may like it. Click the subscribe button and also the little alarm bell if you'd like to be notified of my next episode. With that, farewell until the next episode, and stay safe out there, friends.